Okay. Okay, so last week we figured out how to add two numbers together, right? Using, well, two n-bit numbers together, right? Where the number of bits requires number of full adders or, you know, number of bits square minus a little bit through the Pascal triangle of half adders, right? And we found out that if you're actually adding more than 3 bits, it's actually more efficient to use full adders instead of half adders. So I think in the lab today you're going to be building a full adder and then chaining it together to add 2 bits. I don't think I have you guys do 3 bits because that would be kind of a full day. Because each bit, right, to add, it requires about 19 wires, and all those 19 wires have to be in the right place, right? Okay, so what we're going to teach you today is how to multiply, and let me just grab the image of it before I start yabbering, just to make sure that we're good with the multiplication. Okay, all right, so going back to elementary school again, right? We multiply. This is the long multiplication, right? So this is 25 times 14. We're not going to try to multiply a number that big in binary. But if you multiply, right, what you do is actually you make for each digit, for each bit, right? In this case, a place 10 bit, right? You have one row of things you have to like add to it, right? So this first row is basically the multiplication of this first digit to the top number, right? So 4 times 5 give you 0 with the carry of 20, right? 2 times 4 is 8. That gives you a carry 1. That's where this 100 comes from, right? Similarly, if you multiply 1 to 25, but then what you do, you get 25, but then you shift it over because you know this actually has a weight of 10, right? That's the place, the tens place, right? And then what you have to do is then add those numbers together, right, to get your final result. Everybody happy with this? Okay. So if you're multiplying binary numbers together, you do the same thing. Okay, so let's say we're multiplying 2 times 3. Let's not do that in green. Let's do that in black. 2 times 3, right? So in binary, right, a 2, let's just do a 2-bit, right, is 1 0. Right, it's the same thing as 1 0. And then 3 is 1 1. Right, now if we want to multiply these numbers together, we stack them on top of each other just like we did with decimal numbers. And now we know that these are 2-bit numbers, so there's going to be 2 rows that we're going to have to add together, right? Okay, so the first thing we do, right, is there's 1 times 0, right, that's 0, and then 1 times 1 gives you 1. Okay, right, let's go back and make sure my math is correct. Okay, and then, right, the next row, you just put a placeholder 0 here, right? Then you do 1 times 0, that gives you 0. 1 times 1 also gives you a 1. Okay? And you notice now, oh, now there's an additional bit needed already, right? Actually, in a matter of fact, right, in general, the number of bits you need to do if you're multiplying 2 bits by 2 bits together, right, you need 4 bits to hold the answer, right? Because the highest number you can hold with of 2 bits is 3, right? 3 times 3 is actually 9. The highest number you can hold with 3 bits is only 7. So you need to go up to 4 bits to hold 15, right? Which is, 9 is less than 15. Okay? So now you add these numbers together. 0 plus 0 is 0. 1 plus 1 is 1. And 0 plus 1 is 1. So now you have a 4-bit number, right? And hopefully this is actually 6, right? This is 4, this is 2, right? So you add these numbers together, you actually get 6, right? See, it works, right? So this we can do with the full adder, right? Right, that's the full adder stuff that we already know how to do. You guys are going to build it today. How do we do this? The first step up here. What did I do up here? Okay. I did some sort of logic operation up here. 1 and 0 combined together gives you 0. What is that? It's an AND, right? Yeah. Because, right, 0 times 0 is always 0. 1 times 0 is 0. 0 times 1 is 0, right? Only 1 times 1 gives you 1, right? So this is actually an AND operation, okay? So the logic is that what you do in general, right? Let's say you have a 4-bit by 4-bit situation. You do an AND operation, which is why the AND operation in logic gates is actually a dot, right? Right? You have AND of A0, B0, and then AND of each of these. And then in general, since these is 4 bits, you're going to have 4 rows of this stuff, right? And then afterward, right, you add them all up together to give you a result, okay? So you notice that this is 4 times 4. So in general, there could be 8 bits that comes out of here, okay? All right? So let's figure out, let's keep following this 2 times 3 example, right? How do we construct this, okay? So we need a bunch of AND gates, okay? In fact, we're going to need, for 2 bits times 2 bits, we need 4 AND gates, okay? And this is going to be a little wonky. I'm going to arrange them this way. And put them like this, another one like this, another one like this, another one like this. This kind of look like little teardrops or something like that, okay? The way I'm going to connect them is that I'm going to make my A0 up here, and then A1 up here, okay? That's what my first connection, okay? The second input, right, meaning, so this A is, you know, this, let's just do that, right? So 2, we're going to make that into our A, right? And that's just, in binary, that's a vector of 1, 0, right? And then 3, we're going to make that our B, sorry, our 3, we're going to make that our B, that's, in binary, that's 1, 1, right? Okay. What we're going to do is we're going to put the B, which is the second thing we're multiplying by, on the along the vertical instead. So let's see how this connection is going to be, right? I'm going to put B1 here, and then I'm going to put B2 here. And this is mostly just so we can see it, okay? When you start programming these into FPGA, it doesn't actually matter where you put A's and B's, right? It's just for us to visualize it easily, okay? So, right, in order to get to, oops, not 1 and 2, 0 and 1, you need to start counting from 0, right? This AND gate here, right, corresponds to this AND gate, right? Right? But not only does B0 also multiply by A1, right? So I have to do an AND gate between B0 and A1 also, right? So what I'm going to do is I'm going to have this wire hop over, unfortunately it kind of looks bad, hop over, and then also connect to this other AND gate here, right? Okay. So, and then we do the same thing for row number 2, right down here. I'm going to connect my B0 to my first AND gate, right? And then it's going to hop over whatever that input is and go to the second AND gate also, okay? In fact, right, this A1 here has to go over, oops, that was too short. I'll move this up a little bit, sorry, not enough space, right? Gonna make the connection here. I'm gonna make it hop over here and go all the way down here, right? Because that allows us to multiply, do the AND between A0 and B1, right? Which is A0 and B1, which is this one right here, right? So we need to do all these operations, right? We don't have the 2's because we don't need the 2's because we're doing the multiplication with just 2 bits. But in general, 4 bits, it gets bigger and bigger and bigger, right? Okay? All right. And the last thing we need to do is also connect A1 to B1, right? Because that's multiplying this part, okay? Right? And these AND outputs all comes out, right, as your as the results before you do the addition, right? So A0, B0, that just gives you the result, right? We don't need to do any full adder operation. So let's just have this hop over, and we're going to have a S0. So notice that it's going to be flipped, right? So S0 is going to be here, S1 is going to be here, S2 is going to be here, right? In fact, I'm going to drag this out a little bit longer so we can actually see the full adder, right? Okay. So, right, the result of, okay, let's go up here. The result of this AND gate and this AND gate has to be added together, right? So what I'm going to do is I'm going to pull this, take the output here, right, and pipe those in into a full adder, right, with a carry in of 0, right, because that's the first number we're adding together, so we don't have a carry in, okay? And that full adder output is going to give us whatever S1 is, okay? All right, then, right, now I'm going to switch color. There's a lot of colors going on, right? I also have to add the result of this with this, right? Do I have to do that? No. With 2 bits, I actually don't. So this is the result of B1A1, which is this row here, okay? Right? But what I need to do is actually take that output here, use the carry in from the other full adder, right? Because I'm going to add up multiple numbers, okay? And I need a second number to add. The second number I'm adding, right, is this number, in this case, A0, B2, but B2, since we're only doing 2 bits, but times 2 bits, B2 is always going to be 0, right? Because we don't have a third bit. So in general, what will happen is that you'll keep adding these AND gates until you run out of AND gates, until you run out of bits. But since we know it's always going to be 0, we can actually connect that to ground, okay? Okay, because ground is equivalent to 0 in digital logic, right? And then the result of this will give us whatever S2 is going to be, okay? The carry out of this full adder, remember the full adder? So I'm going to arrange this so this is, input A, B, and this is carry in, and this is carry out, and this is the result, right? Right, let's just call that S, right? Okay. So the carry out is going to be whatever, it's going to tell us what the 4th bit is supposed to be, okay? So you get 2 bits times 2 bits. In general, it can give you 4 bit as an output, okay? You see how these logic gates kind of, once you have the full adder, you can use that, right? And then you put other stuff on top of it to do other operations. Okay. People okay with this? Now imagine if you want to, if you have a, let's say like a, I don't know, and if you have a value for a pixel here, right? You want to move it to a different place, right? And you want to calculate what that is, right? You're probably doing additions and multiplication, right? By translating, a dot from here to here, you're actually adding to the vector, right? But then if you want to scale the vector, right, you're actually multiplying that vector, right? So you can see how this actually happens on like computer graphics and stuff like that, where you have to move these dots around, okay? All right. So in general, all of these well, I'm just showing you 2, right? 2 operations so far, right? In general, these different operations can do other things. So besides just adding and multiplying, it can calculate, it can do differentiation, right? Just like in calculus, you can integrate numbers. You can move things around in an array, okay? I want to switch this pixel with this pixel. How do I do, I can do that. I can do serial to parallel arithmetic. We're going to talk about this, I think, next week, okay? And all of these different types of instructions that you're sending to your circuits, right? These are known as instruction sets. Anyone heard of that before, especially the CS people, right? Talk about instruction set. Another is almost like assembly language, but not quite, okay? Right? So instruction set, right, for each type of processor, I wouldn't say type, each brand of processor, it's not even a type, right, will be different. So for example, Intel processor will have its own set of instruction set. And this instruction set is made of about 20 different type of instructions. There's 20 different type of addition, multiplication, and then add 19,998 to that, and that's the complete instruction set for your Intel processor. Okay, and by writing this, you can do anything you want inside. Well, most things you want inside that computer. So to move things around, to scale vectors, right? To add, to move, copy things from one place to another, right? That's another operation that the CPU actually is responsible for. Okay. I don't know what other operations are there. Like change a sine to a cosine, whatever, right? That's differentiation, right? So you can look at this if you want. There's a PDF. You can. Oh, actually, that's on OneDrive. Okay, but if you just Google this, and then you'll find the instruction sets for Intel, and then for AMD processor, it'll be a different instruction set, and for Mac is actually a different instruction set also. Okay, but that's okay. But as you know, inside your computer, there are other parts besides the central processing unit. I don't know why they call it the executive unit. It's called a central processing unit. So all these instruction sets are actually stored inside your central processing unit. It's kind of like a little bank there. And then whenever your processor needs to, I need to multiply, it just grabs the instruction to multiplication, and it does that, right? When you want to add something, it grabs the instructions for addition, and it does that, okay? And it just does that like billions of times. Well, technically it's doing it 133 million times per second, but in parallel to each other sometimes. Okay. Okay. Even though if you have a 3 gigahertz processor, it's not actually doing things 3 billion times per second. It's actually doing it 133 million times per second, but parallel to each other. Okay. It's basically the reason for that number is this distance. So like inside a computer, signal has to travel something on the order of about 10 centimeters, something like that, right? Up to like half a meter, right? A third. I think probably 30 centimeters is a good number. Let's see if I'm guessing right. Okay. Right. So inside a computer, right? You don't have one, but that one, right? Across is probably like 30 centimeters, right? So information has to go back and forth between these parts. Okay. So how fast does light travel well, how long does it take for light to travel 30 centimeters, right? The speed of light is 3 times 10 to the 8 meters per second. If you want to change this to centimeters per second, right, it's 3 times 10 to the 10 centimeters per second, okay? So the amount of time, so how do I show this timing? So the amount of time for it to travel, right, 30 centimeter, right, is 3 times 10 to the 8 centimeters per second, right? The units work out, right? So, oops, not 8 anymore because we're doing centimeters, okay? Right? So these three cancel out. There's a 10 on top. So this is going to be 10 to the minus 9, right, second, right? So that's 1 nanosecond, right, approximately, okay? And so you can do something every nanosecond, right? So that's approximate, so a nano, right? So the frequency of this, right? Let's say this is your period. The frequency of this is 1 over the period. So this is going to be 1 gigahertz, right? And I guess I estimated this number wrong. There's probably you want something that's 100 centimeters. So there's a reason why, right? Basically your motherboard. So there's this clock speed inside your computer that's usually always about 133 megahertz to about 200 megahertz, and that's usually as fast as the thing can go. Okay. You cannot go over, certainly you don't want to be at 1 gigahertz because there's going to be some delay, right? So this is on the order that is restricted by the speed of light, basically. Okay. I'm sure there are like military systems that pushes to the edge of this 1 gigahertz, but for commercial electronics, yeah, we're sticking with about 200 to 133 megahertz. Okay, and we're gonna see this once we start talking about clocks and stuff. Okay. Okay, but I think the point of this, before I got distracted, right, is that there are other pieces of your computer that you need to talk to, right? Not just your computer is just not is the only thing it has to do is not just adding and multiplying numbers together, right? It has to grab information from your memory, which is usually called what? RAM, right? Random access memory, right? It also has to get information from your hard drive and put it in the RAM, right? So that's where all these little components are. So your RAM is actually located here. It's not good highlighting, right? Right. So your processor is behind this heatsink. Your RAM is over here. Okay. I'm just gonna highlight it, right? Processor is here, right? Your hard drive is stored somewhere back here. It doesn't have to be in the same place. But, right, your video card actually has its own kind of like parallel processing unit in it. So when you're playing video games or something like that, your central processing unit can do a certain operation. Your video card actually has a different instruction set. Its architecture is actually different, optimized for that instruction set. And that's why when you run a game on your video card, it's a lot faster than running it on off a CPU, because it's designed to do all those vector additions and stuff like that, okay, as opposed to just being a general processor, okay? So your central processing unit can do anything. Your video card is only designed to do certain instructions instead, okay? So even though your video card is probably cheaper than your central processing unit, it's actually faster at certain things, okay? And we're gonna see how that comes about, okay? But, so next thing we're gonna talk about is memory, right? In order to do all this computation, right, we need to retrieve information from our RAM, right, and also store information into our RAM, right? Once we did this multiplication, right, we have to store these S1, S2, S3, S0 numbers somewhere, right? And this is where something called digital memory, and then in logic is actually called, they're actually called flip-flops, and it's not what you're wearing when you're on the beach or something like that. Flip-flops are actually the basis of computer memory, even up until now. Okay? Specifically, these things are going to be called D flip-flops, okay? And I want to figure out what this D stands for, right? And a memory bank, just looks like little black chips, right? And that's because all of these are built in a certain way so that they can actually store information when you want it, and then throw the information away, or allow the information to change when you don't need it, okay? And these are called random access memory, okay? The reason it's called random is that, right, when your CPU is trying to access information, you don't want it to have a long line. Oh, only certain information can come out at the same time, right? At a time, right? You want to be able to access all the different parts of your memory all the time, okay? In fact, right, so this is some big memory. I don't even know what size this is, right? This is maybe like a gigabit, right? Gigabyte. Usually you put them in bytes. So there's a billion of these inside this bank, okay? And each of these bank is actually made of transistors, okay? And each bit of memory is actually made of 1, 2, 3, 4, 5, 6 transistors, okay? So this allows us to store 1 bit of information, okay? And we're going to see how that comes about. Don't worry about this diagram too much. We're going to start with a simpler version of it and go through the logic and see why this is the way things are these days, okay? So I'm going to start with this thing called a set reset flip-flop, okay? Hopefully you recognize this symbol. What is this? What kind of gate is this? And it's a NAND gate, and there's another NAND gate on top, okay? And this arrangement is a little wonky, because usually with NAND gates, right, you have 2 inputs that are connected to, as your input, you can flip your switch and stuff like that. But the input for the bottom NAND gate is the output of the first one. And then the input for the first NAND gate is the output of the second one. Now you got a weird catch-22. Anyone know what catch-22 means? right? Catch-22 situation, right? Well, how do I know what the output is without knowing the inputs, right? Because I don't know what, if I don't know the inputs, I don't know the outputs. So there's a catch-22 situation. So let's see if we can dissect this a little bit, okay? So X here, right, is the NAND between A and Y, right? Because this is basically Y, right? Because it's connected by a wire, right? And this and the bottom one, this is X, right? Okay. So in logic math, right, X is going to be the NAND, so the AND between A and Y, and then negate it, right? Okay. Similarly, Y is equal to B and X, and then negate it, right? So that's what the NAND operation is actually doing. Okay. To make this make sense, right, what I'm going to do is I'm going to use De Morgan's theorem. That's why I have you guys derive it, right? When you have a NAND between two things, it's actually a OR of those two things, but the input negate it. Okay. Right. Similarly for Y. Okay. So with this, right, we should be able to figure out what's going on with this little circuit we just built. Okay. What I'm going to do is I'm going to set up the circuit so that I know what the inputs and outputs are initially, and then explore what happens when I change that. Okay. Because there's no way for me to figure out what the output is without knowing the there's no way for me to figure out the output without knowing the output. That makes sense, right? So that's the catch-22 situation. Okay. So I'm just going to start off with a valid state. Okay. I'll just double check this is valid or not. In fact, I'm going to redraw this down here so we can have it next to us. Okay. Right. A, and then the second NAND gate. We're going to have B here. Right. We're going to route this input here. We're going to route this output under here, right? We call this X. We're going to call this Y. All right. Okay. So if A is 0, B is 0, right? Okay. And then if X is 0, X is 1, right? If X is 1, that is sending a 1 over here, right? And this is going to be, if this is also 0, so 1 and 0 is going to be 0, but negated because of the NAND, right? That's going to give us a 1, right? So that's a valid output for Y, right? I'm going to check the other side, make sure this gate also gives me a valid output, right? Since Y is 1, right? 1 and 0, right? Because A is 0, is 0, negate it, right? That gives me 1 as the output, okay? So 0, 0, 1, 1 is a valid state for this flip-flop, okay? Okay, we'll see what happens, okay? So what I'm going to do is I'm going to change the A input from 0 to 1 and see what happens, okay? If I did that, right, so this is 1, B is still 0, okay? So Y, right, since Y is 0, since this is already the previous state is Y, we know that this is going to be 1, this is going to be 1, right, because this directly connected, right? The NAND between 1, 1 is actually going to go to 0, right? Right? Because AND between 1, 1 is 1, right? The negation of that is 0, okay? So that's going to make this propagate back here and make this 0 also, right? Okay, right? So what happened is that when I change A from 0 to 1, it made X 1 to 0. It did the opposite, right? Okay? So, you know, why are you doing this? This is kind of silly, okay? What I'm going to do is if I flip, what happened is that when, let's say I change A from 1 to 0 now, right? If I did that change, I basically just go back to the previous state, right? Let's check, right? So, right, 0 and 1 is 0, right? The negation of that is 1, so this actually, it changes X to 1, right? It just changes this to 1, okay? Right? Hopefully that makes sense, right? I switch A from 0 to 1, it just changes X from 1 to 0, okay? All right, well, okay, that's kind of boring. All right, let's see what happens if I did this to B, right? Right? So if I flip B from 0 to 1, right, that means this is a NAND between 1, 1 now, right, and the output of that is 0, right, and that brings it back here and makes this output 0. Sorry, this input 0. So changing B from 0 to 1 changes Y, right? Okay? It seems like me switching this up and down changes what this is, right? On the opposite, okay? Right? Similarly, if you flip this back to 0, it changes Y back to 1, okay? Pretty boring so far, right? I could have done this with a NOT gate, right? Why am I spending like 6 times as many transistors to do this, right? Okay? Now I'm going to do is I'm going to start with a different state in case you are not already too bored already. Okay? I'm going to start off with, instead of starting off with A being 0, I'm going to start off with A being 1. Okay? And remember, when A is 1, right, this is the valid state for the flip-flop. Right? So I'm just going to copy that down. Okay? All right? But instead of changing A again, I'm going to change B from 0 to 1. Okay? So let's see what these inputs look like now. Okay? Okay, so A is 1. I'm going to make B 0. Okay? And then the starting state, right, is 0, 1. Right? Okay? So that means this is going to propagate over here. Right? So this input is 1. Am I doing that right? Yeah. So the NAND between 1, 1 is 0, so that's still valid, right? So now, right, this stays 0, right? So when I switch, remember initially B was 1, right, and Y was 1, right? But when I switch B from 1 to 0, Y still stay 1. 1 to 0. 0 to 1, you're right. Okay, I wrote it backward. Okay. Okay, let's just double check that it's still true, right? So if I switch B from 0 to 1, right, the NAND between 0 and 1 is still 1. Okay? It's an AND but negated, right? So somehow, right, I'm able to change B without changing the output, right? And this is known as remembering something, right, in binary. Okay? Because, right, a lot of times what happens is that, right, the A's and B might be connected to some input, right? And as long as your A is set to 1, okay, your B cannot change what your output is, right? And this side is storing the information. This is the side that is actually changing all the time, okay? So somehow, if you think about A as kind of like the lock, right? When the lock is on, it locks the output from changing, okay? Okay. This behavior is actually symmetric. So if you actually make B 1 all the time, flipping A up and down doesn't change the output either, okay? So this circuit is known as a set reset flip-flop, SRFF, okay? It's just a lot of acronym, okay? And if you want to represent it in functional form, so the reason it's called set reset, we're going to discuss what that means, okay? Right? You have the R and then the S inputs here, and then the outputs are Q and Q bar, okay? Because what's happening is you can see this here, right? The output here is always going to be like opposite each other, okay? Okay. All right. So the functional thing I want you guys to remember is that, right, when the set here is high, right, the output stays the same no matter what reset does, okay? Unfortunately, these wording, I don't like these wording, right? You can think about the reset as like the changing input, right? And then the set as like, oh, can permit the lock, okay? Okay. But when the set function, the set voltage is low, meaning at 0, right? What happened is that the Q can be changed by set and reset, okay? Whatever Q is, it's going to be opposite of reset, okay? Now the memory is open to be changed, okay? All right, make sense? Maybe? A little bit? Okay. So this was the technology when I bought my first computer in 1995. So this dates how. So these are called DRAMs. Dynamic, is it dynamic? I don't know. Oh, I think the D stands for like dual inline random access memory. Okay, okay. So, you might have skipped this actually. So there's this thing called SDRAM that came out in the late after 1995. These are called synchronous dynamic RAMs. Okay, okay. Synchronous is going to be what it sounds like. You're going to synchronize with something. Okay, synchronize with what? What's the most important thing to synchronize with on the computer? The what? The clock? The clock of what? Uh, of the motherboard, right? So the motherboard actually has this global clock that it synchronizes everything with, not just the RAM, but also with your processor and all that stuff, right? And that's why, right, this is the reason why I was talking about this up here, right? Where, right, your motherboard basically sets this frequency or this delta T so that all the processes actually get synchronized inside your computer so that things aren't just being done in a random place, okay? Right? So, and now we're gonna have to kind of talk about this thing called data packets, okay? So those of you who are not in CS may not be familiar with this, or even if you are, right, you may see this, okay? And these are just some pictures of SDRAM. So this one is actually the back end. I don't know why they show that, but these are SDRAM modules so that you can actually get information out of them. And SDRAM is a little bit different than just regular DRAM, okay? In that, I'm going to try to draw this diagram. If I'm on the right slide, just want to make sure I'm drawing the right thing. Okay, okay, right. What they're trying to do is to synchronize the data information being sent. Okay, so I'm trying to draw a straight line, right? And on the horizontal here is time. Okay, what's over here is what's known as a clock. I'm going to make the clock red. Okay, a clock is basically something that has a regular interval of high and low, high and low, high and low. Oops, that one's not regular. Oh shit, never mind. Okay, I'm going to draw this like this. Make them similar in length, but hopefully you know what I mean, right? It's a really boring thing. It's just going high and low, high and low at a regular interval, right? Maybe in between here is, you know, delta t between here, the period of this, right? It may be 6 nanoseconds, okay? Okay. So what's happening is that, right, when your information changes out of sync with each other, right, maybe doing it at random times, right, like this, right, then multiple processes cannot be happening at the same time, because if your memory is changing right here, right, and your processor is trying to grab that information, by the time that processor finished processing the information, that information could have changed, right? So you don't want that. Everyone should have the same copy of information each time they do a calculation, right? Okay, so what they do, I'm going to go to green here, right, is they want to make sure that these changes can only happen, I already drew the wrong one. These changes can be only happen when the clock is high, okay? You can only do this change when the clock is high, okay? Right? And this is where we're going to start thinking about how we built this thing called clock SR flip-flop, okay? All right, we're getting more and more acronyms here, right? It's the CSRFF, okay? Right? And this is the basic unit of an SDRAM, okay? So the RS flip-flop, already talked about it, right? That's already 2 NAND gates, right? 6 transistors already, right? We're going to add 2 more NAND gates into here. It doesn't have to be NAND gates. We could have done this with XOR gates, but we're going to keep this simple, so because we're already familiar with NAND gates, okay? In fact, right, this Q bar output is actually never important because it's always going to be opposite of Q. Okay, that's why I call it Q bar. So that's why the output is always only connected to one of them. Okay, even though the second NAND gate actually does have an output, we never really connect to it. Okay, right? So this first set of NAND gates, what it does is that instead of just having the R and S input here, what it's going to do is going to have an input from the clock. So the clock, remember, goes from 0 to 1, or in voltage 0 to 3.3 volts, you know, up and down, up and down, up and down at a regular interval. Okay, right? And let's see how the truth table, how this circuit works. Okay, and this is probably the best way to describe it. Okay, so let's say my S and R are both at 0, right? Okay, from the truth table, from the RS thing, from the RS flip-flop, right? That means the outputs are the outputs of these NAND gates are going to be opposite of it if the clock is 0. Okay, even if the clock is not 0, it's going to be opposite of it. Okay, because they're NAND gates, right? It only goes to 0 if both inputs are 1, right? Okay, so that means this is going to be, I'm going to call this input R. Well, they're just being mean to me, aren't they? Let's just do that. Let's call this S. Let's call this R prime. Call that S prime. I don't know why they made the diagram flip like that. Okay. Um, okay. Sorry for that. Yeah, I should have checked this diagram before I pasted it. Okay. But right, if S is 0, S prime is going to be 1. If R is 0, R prime is going to be 1. Okay. Just by the fact that one of these, if one of these input is 0, the output is always going to be 1. That's the property of these NAND gates. Okay. What I'm going to call the output here is that whatever it is at the current clock. Okay. Okay. The output at N is the current output. Okay. And then Qn plus 1 is the output. Okay. At the next clock cycle. Okay. When this pulse comes in. Okay. Okay. What's interesting is that while if you did this, right, if you just change S from 0 to 1, right, the clock is still at 0 and it's holding this output to be the same, right? It's not allowing it to change, right? As long as there's one input being 0 at a NAND gate, right, the output cannot go low, okay? So this doesn't change anything, right? So it stays the same. In other words, Qn plus 1 is actually just Qn. It stays the same, okay? That makes sense? All right. So let's say now we think about, oh, the clock pulse comes in, right? The clock goes high. What happened is that when the clock goes high, right, now, right, this is the clock, right? This input now is 1, 1 instead of 0, 1. Sorry, 1, 0, right? And this flips this from 1 to 0, right? Now that that went from 1 to 0, right, now the output of the RS flip-flop can now be changed, okay? So Qn, we actually don't know what it is, right? Because the reason we don't know what it is because it's locked behind this clocked, right? So whatever it is, we can't change it. I mean, you can look at it, but we can't change it, right? And that's why it's stuck at Qn plus 1. Sorry, Qn. But once, right, this clock pulse comes in, it basically unlocks this RS flip-flop, and now we can change the output, right? And remember that the output, right, is always the opposite of input. Ah, did I do that right? Right. Yeah. Okay. So this is why I think this is going to be S prime. That's why this diagram should be fixed in the future. Okay. Right. So when S goes to 1, S prime goes to 0, right? And the thing is to remember is that whatever the input is for our RS flip-flop, right, or SR flip-flop, the output is going to be opposite of what the input is, right? As long as it is not, the reset is not at high, okay? Okay. And since the reset is at low, sorry, the reset is at high, that means you're able to manipulate the memory, right? Remember that when your input goes high, you're able to actually store information. When input is low, you're not allowed to. So therefore, right, whatever information is over here gets overwritten, and you change whatever it is there. I don't actually know if it's 1 or 0. It's going to be forced to be 1. Okay. Okay. And then if that S goes from high to low again, right? We just went from high to low. While the clock is still high, right? These input basically will match with each other. Okay. Whatever input you place, your output is going to be the same when the clock is high. Only when the clock is high. Okay. And your reset key is set to 0. Okay. Okay. But if your reset key is set to 1, right? This will actually make this a 1. Okay. And if your clock is high, right? That means R prime is always going to be 0, right? When R prime is actually 0, this turns off this RS flip-flop, and therefore it doesn't allow you to write anymore. It stays the same. Okay? So this is blocked, right? Or not able to write, not able to change, right? Okay? So only when the clock is high and your reset, your R information is high, that's the only time you can change the output. Okay? All right. There's also this ambiguous state that goes in undefined, where if you make your input both the same and both high, it's actually undefined, and I'll let you guys work through the logic why it doesn't make sense for it to be like that. Okay, okay, and this is actually ambiguous state, and that will actually, if that happens, it'll probably just crash your computer. Okay, right, right. So since R and S, the input, right, should always be opposite of each other anyway. Okay, what happened is that we're going to make these things called D flip-flop or DFF. Now we shorten things. Instead of allowing these inputs out here to be anything you want, we're always going to make them opposite of each other. Okay, so you add a NOT gate here to make sure whatever input here is opposite of the input here. Okay, and instead of calling this S and R now, we're just going to call it D, because what's going to happen is that D is going to get transmitted to Q when the clock is high. Okay, so D for data, data is going to get transmitted to Q whenever the clock goes high. Okay, right. Let's see what time we got. Well, yeah, I'm a little low on time. Okay, and I'll let you guys work through this truth table. But the basic gist of it is that whenever the clock is low, right, the output cannot change no matter what you do to D. Okay, but whenever the clock is high, then basically whatever D is going to be equal to the output. Okay, when D goes low, the output goes low. When D goes high, the output goes high. Okay, right, right, and this is basically 1 bit of information that's in all our devices right now. All of the RAM in our devices is based on this. Okay, and they make trillions and trillions of these every day. Okay, all right. This may be a simpler truth table where if the clock is low, right, and D is low or high, it stays the same no matter what it is, right? So when the clock is low, you cannot change the output. When the clock is high, that's when you can change the output, where D just gets transferred over to whatever Q is. Okay? Right? And then in a functional diagram, it looks like this, where you just have D, and then you have the clock, and this is your Q, and this is your Q bar. And usually you don't use the Q bar. Sometimes you deal with some registries, and we're going to see how that gets implemented in the future when we actually want the opposite of the output. Okay. Okay. So in our lab, instead of building our own D flip-flop, which will require like 4 NAND gates and then a NOT gate all interconnected to each other, okay, which you can do actually, is not too difficult, but there are actually built-in versions of these these are called D flip-flops, Okay, so each chip actually has 2 bits of memory in it. So the left-hand side is bit number 1, and the right-hand side is bit number 2. Right? This is the 74LS74. So in case you ever need to build your own memory, you can do that. But in our lab, we actually started switching out to using FPGA. So you can actually build these D flip-flop inside FPGA if you want. Okay, as a out of NAND gates and OR gates. And is there anything else? Yeah, just NAND gates and OR gates. Sorry, NAND gates and NOT gates, not OR gates. Okay. In fact, you actually don't really need a NOT gate, right? This can just be not a NAND gate with both inputs being the same, right? That'll give you the same thing. So you can build a lot of stuff just with pure NAND gates. Okay, so let's not go through that too long. Okay, so these are the things that you can actually put them on their breadboard, but I think since last year we stopped using these chips, but you can play around with them if you want. Okay, so those are the basic components of your memory. Okay, instead of building them out of NAND gates, you can actually build them out of NOR gates. Okay, so this is a picture I took somewhere at some point, right? So instead of putting NAND gates, you can actually build these basic memories out of NOR gates and AND gates instead. Okay, now I'll let you guys derive that in the homework. Okay, how this works. Okay, and the interesting thing is that, right? Does anyone know where I'm leading to this? Where I'm leading? What's the next? What's after SDRAM? What do you actually use in your computer? DDR, right? And what does the D stand for in DDR? Or the DDR? What does it stand for? It's already digital. What data? Double data. Double data rate. Random access memory. Okay? And why did I bring this up right now? Okay? So, let me just describe this. Okay? So, for the NAND flip-flops, right? When the clock goes, that's not this circuit, right? For the NAND flip-flop, right? When the clock goes high, that's when the data gets transferred from D to Q. An interesting thing about NOR flip-flops is that the data gets transferred from D to Q when the clock goes low instead. And I think maybe now you start seeing why we only have DDR memory, not TDR memory. How come we can't triple it? Okay, so if you built your memory bank and you built half of them out of D flip-flops and half of them out of NOR flip-flops, and you send in the same clock, right? So if you only build it out of one type of memory, okay, what happens is that as the clock pulses in or out, the only time you're reading and writing to your memory is when the clock goes from low to high, right? So this is for the D flip-flops, right? So what happened is that the clock not only goes up, it also goes down, right? It goes up and down twice per cycle, right? It has to go down, right? So what happened is that if you connect your D flip-flop to the up part, right, and then when your clock goes down, you put in your NOR flip-flops, right? Now you can actually access your memory twice per cycle, right? And this is why, right, there's these things called double data rates, right? And there hasn't, even those, these guys been out for like 25 years, right? There hasn't been a triple data rate because, well, your clock there's no 3 points on your clock you can synchronize with. Okay, so that's why it's always only double data rate. Okay. In fact, these memories are, there's some specification for these memories. So DDR, let's go to the latest generation. I'm not even sure this is from last year, probably, actually. Right, DDR 400, right? Let's see. So the cycle time is 5 nanoseconds. That means it runs at a clock rate of 200 megahertz, right? So this is probably the fastest consumer electronics we're dealing with. And it can transfer, right, 3,200 megabytes. So multiply that by 8, by 8 per second of bits of data that can actually be transferred. Okay, and so that's how, you know, all these RAMs gets built. Okay, just with NAND gates, right, for synchronous data, right, and then NOR gates and AND gates if you want to do the double data rate thing. Okay. Okay. I think that's it for today. Any questions when I stop recording?